his talk will actually be about using Rust as a Python developer. So we're looking forward for that. Thank you.
1 second, please. Okay, there we go. All right, so as we just said, I am going to talk about why I think you as a Python developer should learn Rust. Even if maybe you don't think you're ever going to use Rust, I think it would be useful. But yes, first, a little bit about me. My name is Daniel. I'm a software engineer at Sentry, which is this error and application monitoring platform. I've been there for about 2 years, and when I started, I was working exclusively on maintaining the Python SDK. But after a few months of working there, I started to learn Rust so that I could take over maintenance of Sentry CLI, which is written in Rust. And so basically in this talk, I kind of want to share my insights of what it was like for me to learn Rust as a Python developer and sort of why I think it's useful for Python developers to do in general. So I'm going to structure the talk as follows. First, we'll talk about just high-level differences between Rust and Python. Then I'll get into some of Rust's unique selling points, which are its safety and reliability guarantees, and also its tooling, which I think is really cool. And then lastly, I'll sort of tie that all together into why I think you should really invest in learning Rust. So this is probably like the main takeaway I would like you to have from this talk, is that it's like the fundamental philosophical difference between Rust and Python. So Rust is a compiled language, and basically at compile time, Rust is surfacing a lot of problems, which in a language like Python could end up turning into runtime errors. So basically, you have the compiler preventing entire classes of runtime errors, which are possible in Python. And because of this, you cannot run into similar errors in Rust. One example is with null safety, and I think Rust does a pretty good job of this. So basically, we could imagine you have this Python code here. You have these two variables, A and B. And then maybe you have some code, maybe a bunch of lines of code between where it's defined and where you actually use the variables. And perhaps you think that something's going to happen where A gets reassigned to an integer value. But for whatever reason, in this case, it didn't. And so we arrive at this comparison of the two values. And there we get a runtime error because you cannot compare a none value with an integer. In Rust, on the other hand, this would be a compile error. And to see why, basically, you need to understand that in Rust, you can't just set any value to null or to none. It has to be explicitly defined as a different type called option. And only then can you actually give it a value of none. So in this example, we set A to be an option integer of none and B to 0. Then if we have this comparison, we will get a compile error because A and B have different types. In fact, even if you reassigned A somewhere, you would get this same compile error. That's because Rust actually forces you explicitly to check that this option value has a real value inside it that you can use. And this is sort of how you would do that. So if A remains unchanged here, you would just skip the comparison, and only if it got an actual integer value would you print that comparison. So essentially, because Rust is forcing you to handle all of these cases, it might require more upfront effort to write code or write Rust code in some times. But the payoff you get for that is that you'll have fewer errors at runtime. So that brings me kind of more into going really in depth into some of these safety and reliability guarantees that Rust offers. Of course, we already just saw that null safety. But another thing I really like about Rust is the approach to explicit mutability. So in Rust, by default, any variable values are immutable, and you can only mutate values that are declared explicitly as mutable. So kind of you could see the benefit of this with this Python snippet here. Let's say we have a list, and Python, of course, lists are mutable with 4 numbers in it, 0, 1, 2, 3. Then we pass this list to a function that I'm calling mystery. The reason I'm calling it mystery is because we don't have access to its implementation, and we have no idea what it does. So what we're interested in knowing is what is the value of numbers at the end of this code, like what is getting output. And of course in Python, we have no idea because mystery is getting numbers and it's able to mutate that arbitrarily. There's no restriction from the Python interpreter or from the language. If we try to write an equivalent snippet in Rust, we might write it like this, where we have numbers equal to a vector. Vectors are sort of the equivalent of lists in Rust. They're growable, mutable, but we don't declare it explicitly as mutable in this case, which is very important because when we go to pass it to our mystery function, we're passing it with this and sign, which means it has an immutable reference, which means that when we get to the print line, we actually know for sure that the output here is 0, 1, 2, 3, because mystery doesn't have the permissions to modify anything in the numbers vector. So if we want to be able to mutate a variable, we need to declare it as mutable explicitly, which we do with this handy mut keyword here. So then we can mutate the variable, but so you might think, okay, now we don't know what numbers is when we print it, but you'd be wrong because, of course, we're passing by reference, and that reference is also not declared as mutable. So only with this final snippet do we have sort of an uncertain output here for what numbers could be. And I think really the benefit of this is that in Rust, you can't have code that is unexpectedly changing values that you expect to remain constant, because you can enforce this immutability through the compiler and the language. All right, another concept that I think is very interesting in Rust and plays into one of its other advantages, which is that it's very performant, is this concept of ownership. And what ownership allows Rust to do that I think is really cool is it allows it to be memory safe while at the same time not requiring a garbage collector to clean up old references. And then we also have these borrowing rules, which I'll get to a bit later. But first, let me talk about ownership. So here we have some code. We're defining hello. We're assigning it to this string, hello world. And what this string from here is doing is it's creating a heap allocation. So this string is mutable, growable on the heap. And because we're creating it here and assigning it to hello, now hello is the owner of that string. And there is always exactly one owner of any allocation, any memory allocation in Rust. And when the owner is done, basically when it goes out of scope, that memory is automatically freed. So it's not like in C where you have to put in these free statements, and if you forget, you get a memory leak. Rust compiler is going to take care of this automatically. So here we have hello. Hello is owning this string. Then we pass hello to foo. And notably, we don't have that little and sign here, so it's not as a reference, but we're actually indicating here that we want to transfer the ownership of this allocation to foo, so that foo can do whatever it wants with it. But as I said, we can always have one owner. So when we transfer the ownership to foo, this hello does not own the string anymore. And this is really important because if you would try to run this code, you would get a compile error. And the reason is, of course, here we're moving hello to foo. And then when foo is done executing, that memory allocation is going to get freed because hello will go out of scope. Foo drops the allocation. And so when we come here to this print line, that reference, that memory is actually invalid, so you can't use it anymore. If you wanted to be able to do something like this, there's sort of two ways you could fix the problem. The first one would be to add a clone, which basically means, okay, I want a new memory allocation that contains the same data. So here we're actually cloning all the characters in memory, making a new allocation, and we're giving ownership of that new allocation to foo. So that way, when we go to the print line, we still have ownership of our copy. Another thing you could do is basically use borrowing, which means that's like an explicit way where you can say, okay, I want this other code to be able to use the memory referenced here in some way, but I'm not transferring ownership. And the way you do that is with this pass by reference end symbol that we had earlier. And I also changed the function name because having this changes the signature of the function as well. So a bit more about borrowing. Basically what borrowing is it's a way to share data with another part of your code without transferring ownership. And so the compiler, because we always drop the allocation when the owned data goes out of scope, the compiler is going to ensure that any borrows are have a shorter life than the owned data. The owned data always needs to outlive the borrows. The compiler ensures this through some fancy methods, which I'm not going to get too much into this talk because it would take a long time. But basically here what I want to talk about is sort of the different types of borrows, because again, going back to this concept of explicit mutability, we can have immutable borrows and we can also have mutable borrows. So here we have the two snippets we already saw earlier with this numbers vector. In the first case, we have an immutable borrow, and in the second case, we have a mutable borrow. Both of these snippets compile because you can always have just a single immutable borrow or a single mutable borrow. But let's say you want to have multiple borrows for whatever reasons. You want to share this one owned allocation with multiple different parts of your code. Is this possible? And the answer is that it depends. So in the case of immutable borrows, this is totally fine. In this code, we have the numbers vector again. And then here what we're doing is we're getting we're getting a reference to the first two numbers in the array. So these, it's going to point to the same part of memory. And we're getting, of course, an immutable reference. Then we're going to pass, so that's the first borrow. We have first two numbers, and then we're going to print it here. So this first borrow lives this long, basically. And then we also have this mystery function again, where we're going to pass numbers to it. That's the second immutable borrow again, because there's no MUT after the AND symbol. So this is perfectly fine to do because Again, mystery cannot mutate numbers, so nothing could happen to first two numbers in the meantime that would invalidate its immutability. But let's say you try to do something like this, where you again get this immutable reference, immutable borrow of first two numbers, right? So we would expect when we print it here that we will print 0, 1 because we are getting an immutable reference to those values. But here in the meantime, we're passing a mutable reference of numbers of the whole vector to mystery mute. And of course, that's a problem because mystery mute might modify those values, those first two values in numbers, which would invalidate the basically our expectation that that's supposed to be immutable. What about the case of multiple mutable borrows, you might be wondering? That's also not okay. And the reason why you can also see here is that, let's say mystery mute shrinks the vector so that we don't, like, those first two values are not even in bounds anymore. Or maybe it grows the vector so much that we need to actually create a new memory allocation and the original one is going to be dropped. Then trying to access the first two numbers could even lead to a segmentation fault because maybe our process doesn't even have access to that memory anymore. So we can always only have one mutable borrow, or we can have as many immutable borrows as you want in Rust. Yeah, that's what I just said. Then another thing I want to mention, because I think it's quite cool, is this concept of fearless concurrency in Rust. And don't have too much time to go into it, but basically the compiler is able to ensure at compile time that if you have any data getting shared between threads, that you're using thread-safe types. So you can, it's really, like, you don't have a lot of these concurrency bugs in Rust that you might have in other languages because the compiler just is making sure that you've written that code correctly. Yeah, so now I'm going to talk a bit more about Rust's tooling because I think it's also quite good and it helps you a lot with learning the language. So we have really good compiler errors and warnings that you can also see directly in your IDE, consistent formatting, and sort of the main point I want you to take away is that all of these tools are standardized in Rust. So it's not like in Python where we have like a bunch of different linters and formatters. It's really consistent across the whole ecosystem. So let's take a look at compiler warnings. This is, again, the same example I showed. And if you try to compile this, this is the warning you get. And it looks a lot like what I wrote on my slide because I actually, like, the slide was inspired by this message, but I think it makes it very clear what the problem is and also is trying to help you to understand and learn how you could fix it. The other thing I really like is the Clippy linter because it has a bunch of standard lints that are enabled by default. They're always adding more lints in every new version of Rust. And it's really helpful to help you learn like concepts in Rust and best practices that maybe you aren't aware of. So let's say you have this function, which we can simplify because we're basically taking a Boolean and then returning true or false depending on its value. So the linter will tell you, hey, actually, you could just return the Boolean right away. But actually, this isn't as simple as you can get because in Rust, you don't need the return statement. You can instead write it like this. And the linter will also just tell you, hey, do this. And you can apply this suggestion automatically. You can see it directly in your IDE. So this is really cool. And then there's a bunch of lints that are not enabled by default because they're a bit more opinionated. So you can enable these, and then it makes code review a lot simpler. Like what we heard from the previous talk, you can automate a lot of rules and best practices in Rust. So you would just avoid all these arguments in code review. Same thing with the formatter. Here we have a very ugly function. The formatter would just fix it to that. So Again, this is really cool. You sort of avoid having to look for formatting stuff in code review. And the formatter is also opinionated. So if you tried either of these, which look a bit different, you have the brace on the next line, or you split the arguments to separate lines, the formatter will tell you, no, this is the canonical way to write Rust code, and it will enforce this. And I think this is really valuable because you, again, avoid disagreements. You have a consistent style guide. And because basically all Rust projects use this, you will get used to seeing always the canonical form of Rust, which I think is quite cool. So this brings me sort of to my conclusion of why really you should learn Rust. And I think the first reason is just to gain the additional skill set. Rust and Python are both great languages. They both have advantages. And when you know both of them, you can optimize by use case. So Rust, I would recommend when you have something performance critical, when you need it to be very reliable, like you want to avoid runtime bugs, and systems programming, like any low-level stuff, it's quite good for. You, again, potentially have more upfront effort, but you'll have fewer bugs at runtime. Python, on the other hand, for quick iteration, it's great, simple scripting. And I would also add for data science, I think Python is really powerful because it has all of these data science libraries available. So it has a really good ecosystem there. You, again, maybe you can write it more quickly, but the reason you can write it more quickly is because you're not forced to handle all the edge cases that Rust would force you to handle. So that's something to keep in mind. And then the other reason I'd recommend learning Rust is because when you learn Rust through the sort of the official resources, it spends a lot of time to explain the safety concepts that the Rust compiler enforces. And a lot of these safety concepts are good practice also when you're writing Python code. Like thinking about null safety, of course, this is something you should think about when you write Python code. And I would argue it's even more important to think about it when writing Python than when writing Rust. Because in Python, you don't have the Rust compiler there to watch out to make sure you don't screw something up. So yeah, I would say learning Rust helps you write better Python code. And that's the point I want to leave here is basically, even if you're never going to write Rust, if you at least sort of make some effort to learn at least the safety concepts from it, I think you will be a better Python developer as a result. So if I've convinced you, then please check out this QR code. I've made like a little landing page for this presentation. You'll have the slides that I just presented. You'll also have a link to the Rust programming language, which people also call the Rust book. It's the official resource for learning Rust, and I think it's really quite great for learning the language. And then I also wanted to do a little quick shameless plug because my company, Sentry, is hiring. Specifically, my team is looking for senior software engineer to work on the Python SDK. It's based in Vienna or also in Toronto, but I guess Vienna is more interesting for people here. And there's a bunch of other open roles too, so you'll find at the same QR code, you'll also find the links to apply, and then we'll know that we met at the conference, basically. So yeah, that's it. Does anyone have any questions?
All right, I already see a question over there.
One, two, three. It works. Thank you for the talk. Like, if you have one or maybe two, what were your like mind-bending concept that from Python you had to adapt your way of writing code in Rust? I mean, I have a couple, but I want to know yours.
That's an interesting question. I would say maybe like, in Python you have exceptions, and maybe you have sometimes this like concept of you can try something, like try to see if it's in the dictionary, and if it's not, you handle it in an exception, so that this kind of pattern doesn't work in Rust because you need to check first, basically. The other thing I would say, which I did not mention at all in this talk, is lifetimes. Look into it. It's kind of a hard and scary topic when you're starting out with Rust, but I think it's less scary than you actually think, and you can get used to working with it.
Are there other questions? I see a hand raised in the middle here.
Yes, I wanted to ask, let's say you have a Python program, application, library, whatever, and you have a performance critical part that you want to implement in Rust. Do you have any recommendation on how to approach integration?
So I have not really worked with this interfacing Python code and Rust code together, because my experience with learning Rust was that I used it to work on a totally separate code base that was totally in Rust. However, I'm aware there's Pyo3, which is some project that is making sort of Python and Rust bindings. So I would recommend that you look into that, because there's probably also talks on Pyo3 that you can see online.
Thank you. Are there more questions in the audience?
Dinosaur.
What is your favorite dinosaur? Was the question?
Is this because of my GitHub handle? So that's just the nickname that my swim coach gave me when I was swimming. So I don't have much interest in dinosaurs. I made my GitHub when I was probably 12 or something. I don't know. I didn't expect to use it professionally.
When I was 12, it didn't yet exist. So, yeah.
Oh, what, the dinosaurs didn't exist?
Yeah. Neither. GitHub nor dinosaurs. I would have another question. What do you think of static type checkers for Python? Is this something that is a nice middle ground, or?
I mean, I would use type checking in Python if I was writing Python, but I have to admit, I really got convinced about Rust advantages through learning it. So when I use Python types, I do get frustrated, because it's just very clearly built on top of something that was not designed, I think, with types in mind. And so when you use Python types after using Rust types, it feels harder in a way, So I would say, yes, it's probably better to have typed Python code than not, but it's still...
It doesn't bring you all the advantages.
Yeah.
All right. So thank you very much. And yeah.